Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to look at a general form of resonance for a variety of PET functions. So we are going to consider a second order differential equation with different kinds of right hand side and explore the kind of problems that are going to arise when the case of a resonance arises. Let's go ahead and take a look at the mathematical detail of this situation. So here I have description of a recipe which is very similar to what we did in the previous lecture with the case of the pure resonance of an oscillation. The approach is all very similar. This is more mathematical than what we had considered before. The previous example is what you actually encounter in many applications. This is to make the mathematics of it general. So let's see what are the issues. We are trying to solve a second order differential equation. Right hand side, we said we are limiting ourselves to PET functions for simplicity. The recipe goes like this. First, you strip the right hand side away, replace it by 0 and call that a homogeneous equation. You go find YH, which is the solution of the homogeneous equation. Then, to find the general solution of this equation, you're supposed to write Y particular, which is a solution of this equation. Our approach was to take the right hand side, generalize it. We called it the family of this right hand side. We talked about it last time. And that entire family has a set of undetermined coefficients. Our objective was to go ahead and find those coefficients. But sometimes that approach does not work. And that's exactly the case of resonance. The remedy is the following. If a term of the solution in YP is what appears in YH already, if a term of YP is a solution of the homogeneous equation, this equation, then we have to start with T times our starting guess. If this also has the same problem, that the term here is a solution of the homogeneous equation, then we have to multiply by another factor of T and then consider that. Might look a little bit confusing, so let's go ahead and consider several examples and see what the situation means. So here I have written a simple example for us to work on, and just to show the issue of resonance and how the solution differs, I have one case where we are going to have resonance. So this is the case of resonance or mathematical resonance, and this is case of no resonance. No resonance we had seen before. Let's go ahead quickly solve that just to refresh our mind as to what our approach was. Our approach was first consider the homogeneous equation. Homogeneous equation, you just strip the right hand side, the forcing term is taken out, so you have y double prime plus 3y prime plus 2y equal to 0. Of course, we go ahead and write the characteristic equation of it. We solve that, that's easy, so I get my minus 1 minus 2. I write solution of the homogeneous equation, which is some factor of exponential of minus this r times t and the other one times t. Okay, then so this is a solution of the homogeneous equation. How about this one? We said we go ahead and form the general family of this thing, or the undetermined coefficient version of this thing. So we are going to call that, let's say, YP, Y particular. We started with just straight family of this. We talked about what goes here in the last lecture. we notice there is nothing similar between the terms here and the terms there. That's what makes it to be no resonance. If a term here also showed up here, that's a case of resonance. We have to take some extra steps. That's what we are going to see in this example. This is exactly like what we have done before, that we take this thing. So I take yp, I take my derivative of this, so that's obviously just c. Second derivative of this thing, well, easily 0. We are going to combine these things into our equation, which is 1 of this thing, 3 of this thing, and 2 of that. And this combination is supposed to reproduce the right hand side. So 1 of 0, so that's rather pedantic to write, but 1 of 0, and 3 times c, and 2 times ct plus d. This is supposed to reproduce 5t plus 7. We see that this is quite possible. Simply we have to find what c and d is going to fit the mold. So I have here 2ct plus 2d plus 3c. That is what has to be 5t plus 7. So 2c has to be 5, and 2d plus 3c has to be 7, which you go ahead and solve, and perhaps you get c is equal to 5 halves. Plug it here, so it becomes 15 half. Take into the other side makes minus 1 half. Your d becomes minus 1/4, I believe, so you double check that. So our particular solution, then the ct plus d, became 5 halves of t minus 1/4. And then we said the general solution is the homogeneous solution plus the particular solution. So homogeneous, we just copy a exponential of minus t plus b exponential of minus 2t, and this one tags along 5 halves of t minus 1/4. That is the general solution of this differential equation. So this was not eventful. This was exactly what we had seen before. Nothing new to report here. But if you modify one term slightly, things changes quite a bit. For example, here I have taken 2y out, and I have this equation, y double prime plus 3y prime is equal to same thing. At the beginning we might go ahead and say, well, let's just do that, and then when we try, there is no possibility of finding our c and t. There is no such thing that's going to do the job. That's the indicative case of resonance. Let's see what are the red flags that tells us something different needs to be done. So same as before, we do homogeneous equation. So homogeneous equation, we have stripped the right hand side off. Characteristic equation, r squared plus 3r is equal to 0. Solutions of this thing are not new, 0 and minus 3. We write homogeneous solutions, a exponential of let's write it out so that we see what's going on, plus b exponential of minus 3t. Okay, looks peculiar, but that's our solution. So if you want to simplify, remember exponential of 0 is just 1, and the other one, well, exponential of minus 3t. Of course, we typically just don't write the 1, which is a plus b exponential of minus 3t. But we have two fundamental solutions. One is constant, and the other one is exponential of minus 3t. Then we come and say, if we wanted to apply this recipe, we would have started with yp is equal to ct plus d. The red flag is here. The red flag says, look, this a term of your particular solution is already present, is a component of yh, meaning d as a constant by itself is a solution of the homogeneous equation. If a term of the particular solution is a solution of the homogeneous equation, then that function is not going to reproduce the right hand side for you. Meaning, if I take this thing and go through this process, I'm going to hit a snag, and C and D cannot be found. So here, to make it more clear, this D, you can think about it D times 1, or just think about this constant and that constant. The fact that these are the same, or the fact that the constant is a solution of this equation, is indicative that the yp is not going to be working for us. So what do we do now? We take this thing, multiply it by a factor of t. So I take t multiplied by my original guess for yp. So now I get ct squared plus dt. Now the terms here are not the solutions of the homogeneous equation, because the solutions were either constant or exponential. These two are neither constants nor exponentials. The commonality between this and that is erased. What we do now is that we take this as our starting guess instead of yp, and we proceed like that. So what do? We take our derivative. So the derivative of this thing, of course, 2ct plus d. We take the derivative again. It's just 2c. We combine these. Well, how are we supposed to combine? According to our equation, one of this thing and three of this thing, and none of that are going to be combined to produce the right hand side for us, which is 5t plus 7. So now we come and say 1y prime, that's just 2c, plus 3y prime, this is 1y double prime, I should have said, 3 of 2ct plus d. Well, I don't have any y's in this equation. That is supposed to produce the right hand side for me. That was 5t plus 7. So I simplify this. It's a 6ct plus 3d plus 2c is 5t plus 7. No, it proceeds just like this case. 6c has to be 5, and 3d plus 2c has to be 7. 2by2 equation easily solved. So I figure out c is 5, 6. Figure out the c and plug it here. So that's going to be 10, 6. That's going to be 5 thirds. Subtract from 7. So that's going to be 16 thirds. Divide by 3. So if you go through this detail and make sure I'm not making a mistake. So it looks like I get d is equal to 16 ninth. So our y particular, which was, or our y, however you want to call it, our y was c, what was it? The y we picked. This is what we started with, ct squared plus d. So that was 5/16 of t squared plus 16/9 of, 5/6. Correct that. So the general solution now becomes the homogeneous that we had plus this solution that we got now. So homogeneous was what? Homogeneous was, this was homogeneous, a plus b exponential of minus 3t. And now this one tags along, 5/6 of t squared plus 16/9 of t. You see that the main thing is that the additional pieces here have a factor of t extra over that one, and of course different coefficients. So this is an example of a situation where it could happen where we classify it under the title of resonance, even though in physics and engineering circles they don't pay much attention to this case. They look at the previous case and some other similar cases like that. So let's go take a look at another example so that this becomes clear as to what we mean that the term of the particular is a solution of the homogeneous. And when that happens, you have to take a step, and the step in all of these cases is to multiply your starting guess by enough t's until that commonality is gone, and then you start. So let's take a look at another example. Suppose I have y double prime plus 3y prime plus 2y, and now let's take 5 exponential of minus 2t. I'm not going to run a parallel here. You have seen enough of those, so let's go ahead and quickly solve this one. Let me see if you can go ahead and solve this thing with the same method that we had in the previous case, and then you come back and compare your solution versus the solution that I'm going to find. So just take a minute to solve this thing. Let me see if I can convince you to go ahead and pause this thing for maybe 5 minutes or so and come back and compare your answer versus what we have. Okay, so we said we go after homogeneous, which is just like last time, 3y prime plus 2y equal to 0. Characteristic is we did this thing long time ago, so I'm going to write that quickly and move on. So solution of the homogeneous, we obtained that easily. It's exponential of minus t and exponential of minus 2t. Great. Now normally, to solve the equation, we would have come and looked at the right hand side, generalize this thing with undetermined coefficient, or we called it the family of the solution. Well, the family of an exponential was general multiple of that exponential. We would have considered c times exponential of minus 2t. Okay, for those of you who started and moved ahead a little bit, perhaps you got stuck at this level. What is the issue here? What's the red flag here that indicates there is a case of resonance to be considered? Here's the red flag. Or maybe again you want to pause and think about this thing for a second and tell me, how do we know that we are dealing with a resonant case and we have to take extra action? What is it that we notice? Here's what we notice, that a term of your particular solution is a solution of the homogeneous. It doesn't matter what coefficient you have, but the function is duplicated. If a function here is duplicating one of the terms here, that means we have a case of resonance. That means this, if it's rather obvious, if I take this thing and plug it here, I get 0. I'm not going to get exponential of minus 2t, so I know before I start this is not going to give me the answer. And here is the solution. Instead of that, you take it and multiply by enough t's. You start multiplying by 1t. Okay, now you compare this thing against the terms that you have there. Well, this doesn't match that, and this doesn't match that either, meaning this is not the solution of the homogeneous, and it's safe to start from here. If we still had a match between what we have here and what we have there, we have to go ahead and multiply by another factor of t, and that's what this this last term here means. Sometimes you do this thing once and that's not enough. You have to multiply a second time, and if it was a higher order equation, you have to keep multiplying. There is a way of making this thing all concise, but it becomes mathematical. So right now we are just going to solve it by examples. So this is what we have to start. Okay, no problem. So we go ahead, differentiate this, and then we have to differentiate again. So we prepare our grounds for doing that. Derivative, carefully apply product rule. Do it again. So derivative of this one now is minus 2c exponential of minus 2t. Product rule again, minus 2c exponential of minus 2t, and now becomes plus 4ct exponential of minus 2t. Is that right? This minus 2 times that minus 2 gives us this plus 4. Okay, now I have to combine these. How do I combine it? According to the recipe we had 1, 3, and 2. So I'm going to take 1, 3, and 2. So one of this, notice that these two double up, so that is just minus 4c exponential of minus 2t. It always happens like that. 4ct exponential of minus 2t. So that is this term. 3 of the middle, so 3 of c exponential of minus 2t minus 2ct exponential of minus 2t, and 2 of this, 2 of ct exponential of minus 2t, and our promise is that this can reproduce the right hand side, 5 exponential of minus 2t. Now you look at this at the first sight, it looks rather peculiar that such a lengthy expression is going to condense to that, but the magic of this is that yes, it does. If you notice, I have 4 of these things here. 3 times minus 2 is going to be minus 6, and then plus 2 here again. 4 minus 6 plus 2 is going to all cancel out. All I have left is this term and that term. So when you simplify, it becomes minus 4c plus 3c. The whole thing boils down to minus c. This whole thing boils down to minus c. And on the right hand side I have exponential of minus 2t. So obviously my c has to be minus 5. So my the function I have to start with, the modified particular solution is going to be minus 5 t exponential of minus 2t, and the general solution we are after is going to be what we started with, the homogeneous. So let me copy that. So that's going to be a exponential of minus t. Let me rewrite this thing. And b exponential of minus 2t, and the additional term that we found here is this. I need minus 5t exponential of minus 2t. So this is the presence of this factor of t that strengthens this term to some extent, and it's an indication of a mathematical resonance in the problem. So this was example number 2. Let's do another one for a good measure for the last example, and hopefully that makes it clear as to what happens. In this example we are going to take a look at this extreme case. Doesn't happen all that often, but it's kind of a resonance built into another resonance. Let's see if we can make sense of that for you. So here is the example. So we want to start with another problem. Y double prime minus 4y prime plus 4y is equal to, now let me write something here. Let me see if you can guess. What should I write on the right hand side that will create that resonance? Let's see. Remember, if your input external force, or if the driving force matches the solution of the homogeneous, that is, the function that you have here is similar to how the system is going to react by itself, then you have resonance and something interesting is going to happen. So Let me see if we wait for you guys to think. What should I write on the right hand side of this so that we actually have resonance? What do you think? It has to be exponential of 2t here, because the solution of the homogeneous, so the reasoning is this: go ahead after a homogeneous equation, which is the system by itself without any external stimulus. So we strip this thing off. By itself, I have r squared minus 4r plus 4 equal to 0. Well, this is that peculiar case that we had the double root or root of multiplicity 2. When we solve these things, you remember we said this has already a built-in resonance. Y homogeneous becomes a exponential of minus 2t not minus 2t, just 2t. And then what was the second term of this thing? Do you remember from quite a few lectures ago? What was the term here? You remember? It had, that one already had the factor of t. Okay, now you say, well, what is the particular? You take this right hand side, convert it to undetermined coefficients. So that's going to be some other constant, say c exponential of 2t. And here's a red flag. This thing is already there. That is responsible for 0. So that definitely is not going to reproduce that. So that goes out the window. Then what was our recipe? Recipe was to go, okay, take this thing, multiply by t. Now here's the funny thing, that this one now matches this one. So that is out of circulation too. So we have to go up the ante every time that what we have here matches one of the terms in homogeneous. Then that's not a candidate, because that reproduces 0. It cannot reproduce this one. So we go one level higher up, c t squared exponential of 2t. Okay, so the trial solution, or the particular solution you are supposed to start with, now we had to go through 2 levels of this thing to avoid the coincidence. Now if I take this and plug it in that, I have a chance of reproducing the right hand side. Let me ask you to do this thing. So take this. So again, one more time, let's see. We pause to give everybody a chance of learning by themselves as opposed to watching me do that. So you take that equation that we have, plug it into the equation, and try to adjust c. Adjust c until this is born. Okay, so take 5 minutes of a break and do this. I'll go ahead and write that, and you come back and double check that you got it right. So get ready for several product rule. So I have y is equal to ct squared exponential of 2t. That's my starting function. I differentiate it, so it becomes 2ct exponential of 2t. That's the product of t squared, product of this one. Do it one more time. Derivative of this one is going to be 2c exponential of 2t. Derivative of this gives a factor of 2. Now I go here. Derivative of 2 squared is 2t. So it becomes 4ct exponential of 2t. Notice this becomes an exact copy of that. Always like that. And then finally I have 4ct squared exponential of 2t. Combining these things was according to one of this, minus 4 of that, and then 4 of this one. It's always better to do that in your head as opposed to writing it down, but just for sake of completeness I write it down. So I have to take this minus 4 that plus 4 of that and see what happens. It makes our writing to form up, and it's kind of not necessary, but well, we write this thing 8ct exponential of 2t. This one is 4ct squared exponential of 2t. So this is 1 of all of that minus 4 of all of that minus 4 of 2ct exponential of 2t and then plus 4 of that. What is supposed to do for us? This is supposed to produce 7 exponential of 2t. Again, same mystery. How is that such a lengthy expression boils down to such a concise expression? Very easy. You see, I have, let's take a look at t squared. I have 4 of them here, 4 times 2 minus 8 of them here, and then I have so 4 minus 8 plus another 4, so of course they are going to all cancel each other out, and then I have 8 of this t exponential of 2t's. 4 times 2, that's also 8, so this blue and that blue are going to cancel each other out, and this is the last man standing, so to speak. This is just what is left here is 2c exponential of 2t. That's all that's going to be left. All of the rest automatically cancels out, so I do have a chance of making two sides equal to each other. I simply need to take c to be 7/2. Well, that means this trial solution that we had is going to be 7/2 t squared exponential of 2t, and then what? The general solution is going to be the homogeneous, which was itself the homogeneous itself had a resonance bt exponential of 2t, and now the additional term is 7/2 of now t squared exponential of 2t. So this is one example. We had to go as far as t squared to avoid coincidences, because there was already t over there. Okay, so we looked at these cases. You know, in engineering, the case of resonance that is very interesting is a problem where the right hand side is the pure sine and cosine, and the left hand side does have some resistance in it. That problem turns out to be more mathematically sophisticated and involved than these. So that is part of the project. If you want to do that problem is the following. So suppose you have a spring mass m y double prime plus we had called this one, say no, we had called it c, I guess. Let's see, coefficient of drag y prime plus spring constant k times y, and on the right hand side we have some external force that has perhaps some trigonometric form, cosine of omega t, like that magnetic resonance issue that we were looking at. There the issue is your controlling factor is this omega, the frequency of the magnet that was on the right hand side and moving back and forth. That one is under your control. The question was how to control that so that the response of the system will have the maximum amplitude. Okay, so in this problem, this is also mathematical, but coincides with many engineering applications out there. This is a very interesting problem. It is in your text, is also in a project that I have in case you are interested. It goes beyond the current scope of the course and requires substantial additional algebra. Okay, I hope you follow some of these leads. We are going to go ahead and take a look at some application problems in the future lectures. These are called mechanical oscillations and such. So we are going to go back to those word problems, the application problems, where a situation in a lab is described in plain words and you're supposed to convert it to mathematics. That's called the modeling. You solve the mathematical formula using whatever we have learned so far, and then we still have a third phase where you have to interpret what you have obtained. So some more challenging portions of the course are still coming up. That is the mechanical oscillations and forced oscillations. Okay, until then, good luck and God bless.